today we will start with a new chapter and a very important chapter conceptually, integral forms of conservation equations. When we write conservation equations, by conservation equations we mean mass conservation, momentum conservation, energy conservation like this. We have two possibilities. One is we write an integral form or we write a differential form. The differential form is valid at a point, but in engineering sometimes it is beneficial or useful if we are able to express the equations in terms of an integral form, because what we require is not a point to point variation, but what happens grossly across an engineering device. So then integral form is more convenient. So to write the integral form of conservation equation, what we essentially use is the Reynolds transport theorem, which converts the control mass based approach to a control volume based approach in an integral sense. So the first thing that we will study today is the Reynolds transport theorem. Let us say that you have a system control mass system at time t. And let us say that this is the configuration of the control mass system at time t plus delta t. Let us say that capital N is an extensive property. Extensive property means a property that depends on the extent of the system, that is total mass dependent property. So extensive property per unit mass are normally called as intensive properties or specific properties. Remember, this extensive property itself could be a scalar or a vector. It need not necessarily be a scalar, it is just defined as a property. Our objective is to find out what is dN dt for the system by expressing it in terms of the corresponding change with respect to the control volume. And this objective is very much straightforward. Why it is so needed? It is so needed because this dN dt of the system, imagine that N is equal to the mass. So, we have the law of conservation of mass which talks about the fact that the total mass of a system remains conserved. There is no law which tells that total mass of within control volume remains conserved. So, if we can express the system conservation law for which the foundations are already there in terms of the control volume conservation, there will be some correction terms, and those correction terms we will establish through the Reynolds transport theorem. So, let us say that at the time t, I will try to use as many color codes as possible. The system comprises this blue region and this yellow region. So, we give the name 1 to the blue region and name 2 to the yellow region. So, n at time t similarly n at t plus delta t So, now one important thing to recognize is that when delta t tends to 0, these two configurations are so much overlapping that their common region can be thought of as our region of interest, which we call as control volume. So, 2 we will define as our control volume, and in the limit as delta t tends to 0, the control mass system and the control volume, they almost converge on each other with a little bit offset regions. So, dn dt of the system, by system we mean the control mass system, so this we can split into these two and then write So, we will write it here. This one, this is the total rate of change. So, this we are writing as a sum of this and some correction terms. So, what is this? This one, yes, this is 1, right. So, if we concentrate on this term, what does it physically mean? It physically means that at a given location, which is 2, what is the rate of change of n with respect to time? So, this location 2 being the control volume, plus if this be the control volume and the system is sweeping from the left to the right, it will appear that this is giving rise to whatever is the rate of change of n at 3, this is giving rise to an outflow across the control volume, and whatever is entering at 1 is giving an inflow to the control volume. So, plus rate of outflow minus inflow of the property. Capital N being the extensive property, let us consider small n is capital N per unit mass, which is an intensive property. So, you can write let us take a small volume element within the control volume dV. So, what is the mass of the volume element? Rho into dV. What is the total property? Capital N, small n is the property per unit mass. So, small n into rho into dV integrated over the control volume. So, that is the second term plus rate of outflow minus inflow. So, we will calculate the term rate of outflow minus inflow. So, how do we calculate the term rate of outflow minus inflow? Let us say that there is a control volume, this is an outflow boundary and this is an inflow boundary, just as an example. So, when you have an outflow boundary, let us say this is the velocity v and you define this dA, which I am trying to show with a different color, this dA with a unit vector normal to it. So, what is the volume flow rate through this dA? the component of the velocity in the direction of normal times the area. What is the mass flow rate and what is the property flow rate? This times n, because n is property per unit mass. What happens for the inflow boundary? This is dA, this is the outward normal, and the velocity is in this way because it is inflow. So, the difference between inflow and outflow boundary can be recognized from the algebraic expression from the outcome of the dot product. If the dot product of V dot n eta is positive, then it is outflow. If the dot product of V dot eta is negative, then that is inflow. So, instead of outflow minus inflow, this we can write simply where plus value of this will imply outflow and minus value of this will imply inflow. There is another subtle point that is missing till now, is that what is this V? Let us say that this control volume is moving towards the right at 1 meter per second, and this control volume can move, it can deform, it can do anything. So, let us say that the control volume is moving towards the right with a particular velocity, say 1 meter per second, and this water is also coming out of the control volume with a velocity 1 meter per second. If that be the case, then what is the net flow of water with respect to the control volume? It is 0. So, it is not the absolute value of the velocity that matters. For the transport of flux across the faces of the control volume, it is the relative velocity that matters. So, this V is Vr or V relative. So, this is velocity of fluid relative to the control volume. So, to sum it up, we can write the final equation. In the left hand side, system, right, dn dt of the system. So, if we write all the terms together, initially I was writing only this term, but when we write all the terms together, that is we add these two, this is dn dt of the system. Okay. Initially we wrote only this term, that is why I wrote that one, but now that we have added all the terms, this is the left hand side. So, this equation therefore becomes dn dt of the system this is CS, control surface, surface of the control volume. This is known as Reynolds transport theorem. This is such a powerful theorem that any equation virtually in fluid mechanics, any conservation equation can be derived from this. So, in this lecture we will give an example of how the conservation of mass can be defined or derived from this. So, example, conservation of mass. So, in conservation of mass, what is capital N? It is the total mass of the system. What is small n? Capital N per unit mass, that is 1. And what is dm dt of the system? This is 0. By definition, a control mass system is something of fixed mass. Until and unless we are looking for relativistic situations where there is a interconversion of mass and energy, that is not what we are considering here. So, we have this equal to 0. Therefore, we are left with to proceed further. In fact, this is a integral equation for mass conservation for the most general case, right. There cannot be a case more general than this, but let us consider some special cases. Non-deformable control volume. If it is a non-deformable control volume, that is V is not a function of t, in that case we can by our wish bring this derivative in and out. Otherwise, we have to use the Leibniz rule for differentiation under integral sign and make a correction to this. We will see later on that the Leibniz rule itself is a special case of the Reynolds transport theorem, and it is a beautiful analogy between mathematics and physics. See, when the Leibniz rule was developed, it was never developed by keeping in mind about the transport of any species, but Reynolds transport theorem was derived physically on the basis of a conservation law. But we will see later on when we will discuss about the boundary layer theory, we will discuss in a context that how these two are interrelated. But just for the sake here, if V is not a function of time, we can take this time derivative inside, that is number 1, and number 2 is stationary control volume, so that B relative equal to V. So, then you are left with now what we can do is we can convert this term from area integral to volume integral by divergence theorem. So, this becomes so then we are left with integral of okay. We are now left with a situation which in a one dimensional analogy is integral of fx dx equal to 0. Question is, does this mean fx equal to 0? So, we have to very typically assess the situation. Imagine that a function f(x) equal to sin x. Over a period integral f(x) dx is equal to 0, but that does not mean that sin x is locally 0 everywhere. But if we say that integral f(x) dx is 0 for every choice of the domain, then that is possible only if f(x) is equal to 0. So here the volume that you have chosen is arbitrary, your control volume choice is arbitrary, you have not taken a very specified limit, right. When you have taken the control volume choice to be arbitrary, since control volume is arbitrary, you are left with this one, which is another way of deriving the continuity equation. So in the class really we have used 3 approaches of deriving the continuity equation. One is the control mass approach, another is taking a box as a control volume, and the third is this Reynolds transport theorem, and we see that all these converge to the same continuity equation. So far today what we have studied: a general form of integral form of conservation equation and its special application in terms of deriving the conservation of mass or the continuity equation, and we have learnt a special technique of how to convert an integral form to a differential form. This is the skill that we have learnt, and how we have implemented the skill: very simple. Wherever there is surface integral, we convert that into volume integral through the divergence theorem and set a volume integral is equal to 0. Because the volume is arbitrary, the function itself is 0, that gives rise to the differential equation. This is the structure that is under concern. Thank you very much. We will continue with the Reynolds transport theorem related topics in the subsequent lectures.